Welcome back to our next session on designing experiments. We're going to talk a bit about a famous experiment that just happened a few years ago, and then do something hands-on, look at some data, and I have lots more methods, things to talk about if we have time. I'm going to pass this to Parsoon for a presentation. There you go. I don't know.
Wait, okay, went away. Cool. All right, everyone. So today's presentation it's not I don't think it's a research paper, but it's basically an experiment that the NeurIPS community or the new people who actually organize NeurIPS have run to measure the randomness in the peer review process. So the idea behind it is a lot of times, yeah, a lot of times as researchers, we all have experienced this something like feels like arbitrary rejection, where we feel that the paper has value, there is some novelty there, but in the end, we kind of console ourselves that because these are 4 reviewers and these are signed randomly, there is some inherent randomness, and that's why you got rejected. But at the same time, the same peer review process is actually when accepted or the other accepted papers that we see it as a genuine validation of the quality. So there was this mismatch, which was the problem. Now the gap is that despite all this influence that the peer review process have on academia, the process itself is never tested empirically. Like this question was not asked, and this was the study in 2014, I think. And this question was not asked that that what would happen if the same process is run again, or if we change the entire community, keeping the expert distribution same, would we get the same level of acceptance and rejections? And that's what this study was about. Right? And the hook for this study is like, if the final discovery is that the process is actually inconsistent, then it's an alert and alarm for the academy, right? Because a lot of big career decisions about people in academia are on top of it. Okay. So the experiment design is very simple. So they have the program chair, they split the program committee in 2 different halves. And out of all the papers that NeurIPS received that year, 166 papers, which is 10% of the papers, are sent to both communities. And then they compare the results based on the accept and reject for the overlapping papers. Now, there are few design choices that are interesting. Like, for example, they only focus on the binary outcome of what is being accepted and rejected and discard completely things like what was the individual reviewer scores, what was the confidence and the review quality. By review quality, I mean that how much reviewer has actually written about what they liked about the paper, what they did not like about the paper. Right? There is no control group for the area chair effects, as in a lot of these papers are the acceptance and rejection of these papers are decided based on people who are chairing the community. They have a big say on which papers which papers are accepted or not, and there is no control groups that account for these effects. And finally, this is interesting. I actually stumbled upon this WordPress blog from one of the area chairs that it says in the experiment that they have actually independently separated this entire community into 2 different forms. Like it gives an image that there are 2 big halls and there are 2 separate communities sitting there, but that's not the case. Like usually there are around 90 to 92 area chairs, and they all work independently, and the reviewers can get papers from both the halves, both the halves of the split, right? Um, the caveat here is that because the area chairs can de-anonymize and they have the access to the submissions, they can get a hint, and that's what this area chair also wrote about, that they can get a hint that this paper is duplicated. And in the end, their rule was that any paper that is getting accepted by either of the splits is going to be accepted in the conference. So this can also create some kind of bias or a confounding effect on the results. Okay, so here is what the outcome was. So 43 out of this 166 papers had different outcomes from both communities. But this is not complete picture. Let's look at the data in more detail. So what they had is they were said that the acceptance rate for the conference was around 22%. So both the communities rejected around 107 papers. But if we see the agreement at that how much time they actually agree on what should be the papers that should be accepted, the disagreement goes to 57%, right? And this was an alarming number. Uh, yeah, so okay, so let's walk through this. So this 43 divided by 166 is that this total, like what is accepted versus rejected by like where the decision was not same divided by when the decision was same, right? But the what conference had was they told the committees that they need to have 22% of acceptance rate. So now, if we just understand that for what percentage of papers, for example, are accepted by A only in comparison to how many are accepted in total, that's like 21 divided by 21 plus 16, that comes out to around 57%. And there's something, sorry, a similar number is there for the second one as well. So basically, the 57% of accepted papers were rejected by other committee. Right. And a more interesting result is that in the in the blog post, the author says that the actual disagreement is actually more closer to fully random. And this 77.5% is coming by assuming that we need an acceptance rate of 22.5%. And they say that with 95% confidence interval, around 40 to 75% of the paper, which is pretty large because we have the sample set is small, would actually flip on a rerun. So this is very interesting. So like if we had two times communities that are sitting for the peer review, then there is a high chance that you'll get a flip when actually between the two committees. Okay. So now that was the experiment. These are the results. Now what there are two different models that are proposed in the blog post that what can explain these results, right? Uh, so the first model is they call it messy middle model, where say that there are some clear accepts and clear rejects. So these are the models that committee will accept or reject, but there is this messy middle where outcome is essentially random. So it just can be decided based on a flip coin. And for example, in NIPS data, we have around 50% clear rejects. And out of the accepted papers, 7% are clear accept, but the other 93% out of 30% paper is random. So there was one way that they explain this the result from this experiment. The another model that they had is called noisy scoring model, and I'm also a little bit fuzzy on the details here, but I can explain whatever I could understand. So there are two different type of variations that we can see. The one is the sigma between, which is basically the real quality difference across papers. Like for example, if there are 1,000 papers submitted, then some papers will be really good, some papers will be should not be accepted, and there will be a big if I assume that there is a normal distribution or there is a given variation between this particular score. The another score is sigma within, which is basically for a given same paper, if we give it to multiple reviewers, how much they score it. And this is score that is we are getting out of 10. So on an average, for the NURIPS committees, any score that is more than 6.5 tends more towards acceptance. Any score less than 6 tend towards reject, and then in between is where the debate happens, right? So the model is that when this noise versus basically which is the reviewer disagreement on the same paper is higher than the signal itself, that how much the papers differentiate between each other in terms of real quality. In these kind of situations, the cutoff is largely a random number or based on a coin flip. Okay. One thing that I could not understand here is, the scale of distribution can be very small or large. For example, here for sigma within, we are talking about 3 to 5 reviewers. But if the number of submitted papers can be in thousands, so I don't know how they balance this particular difference between population distributions. Okay. So what do these experiment actually gets right? So this is actually a real study, real papers, real reviewers, real stake. And it's commendable that the people who are organizing NURIS could actually run this. There could be a lot of backslash as well. So there's a high ecological validity of the experiment. There is a clean identification that if we believe on the binary outcome, the random assignment can create a natural counterfactuals. And finally, because the outcome was binary about reject or select, it avoids measurement ambiguity because we are we are very certain on how the results are being measured. But in parallel, there are few things that this experiment actually falls short on. The first is, again, there is some benefit of using binary outcomes, but it kind of hides everything behind. Like, for example, maybe there are some papers who are getting close to accepted but got rejected, and then there can be some papers who are close to getting rejected but accepted. So all those kind of effects cannot be seen. And to throw away those effects and this core data and say that just by based on the binary outcome might not be a clear representation of what happens in research community. Then again, this is something I mentioned before, the confounding noise sources. So it is very hard to isolate reviewer and area chair and discussion effects. And then same reviewer or community can underlie in the both the halves, because as these things are organized, they are kind of independent in terms of area chairs. There are 90 different area chairs. And I think all they did is just separated these 93 different area chairs in halves, but not the reviewers themselves. Yeah. Okay. All right. So here are a few questions that I had. Like, is the noise that we are getting in this experiment is random or systematic? And what exactly is the cause for the disagreement? Even though they have shown us few, like in the blog, they talk about two different models, but there also they just say that it's going to be a coin flip and does not actually give us a reason why it should be truly random. Um, and where does the disagreement rise? For example, is it because of the reviewer scoring, or which of these effects are the entire pipeline is basically a black box? And finally, this is the biggest question: is that does this inconsistency actually mean that the process is broken, or is it that we need to actually measure something else to figure out that how meaningful is the process for determining the quality of accepted papers? So coming to threats to validity, as I said, the internal threat is the same that I described. There are different confounding factors. The external threat is that this is a single conference, single year, single field, and may not generalize to different type of communities. And finally, the construct validity is basically what what I mentioned about the scores, that this binary accept and reject scores, and this measures the decision consistency of papers getting accepted or rejected, but the evaluation is much more nuanced metric about what is the quality of research that has been done in a given paper. Okay, so now here are a few discussion points that I had. This is the last slide that I have. That is the consistency in the acceptance and rejection of the paper right metric for evaluating peer review? If not, are there any other metric that we can think about? And should this process actually change how we evaluate researchers in total? Like how much importance should be given to the amount of papers accepted in a given community for a researcher? And is there a possible design for a robust review system? And the fourth one is something that actually is being mentioned. The author mentioned, I think Eric mentioned in the blog post itself, that should we run this experiment on graduate admissions? And are we going to see some similar effects? So I actually chuckled when I actually read this for the first time. It was interesting. Okay. Yep. That's it.
This was a very splashy when it came out. It's the first time anybody has tried something like this, so there's a lot of news.
It was very bold. Yeah.
So this was done for like 1 year of NERP's
Yeah.
submission.
Just 2014 or 16. I forgot the year. Yeah.
And again, you said that the way papers were decided if they were accepted is like if they were accepted by at least one of the two teams.
Yeah, but they did not know that papers were duplicated, and that's where the second post that I shared the link to comes here, because area chairs could de-anonymize and they actually can look at the submission list. They might have done something like nearest deduplicate or anything in the title, but they could still figure out that this is a duplicate paper that is being assigned. Yeah.
But there's some papers that had two chances to get accepted.
Yes, that was another impact. I had this in slide, but I removed it. That there is a fairness argument there that for these 166 papers, the chance of acceptance actually increased.
Yeah,
Yeah.
it's like random aside.
Exactly. Yep.
Yeah, so
So that year is unadjusted.
you would want to be in that group, right?
Yeah.
Yeah. That's right.
Yeah. Yeah. I also find this score really close, in the noisy scoring model. This I don't have the real data how it's coming from, but more than 6.5 accept and less than 6.0 on an average reject is like very close boundary. I kind of assumed that in the reviews this would be like much wider, like maybe something 5 versus 8 or something more. Yeah. Okay.
The interesting bit to me is that, except for the clear accepts, which is the top 7% of
Yeah.
papers, and the clear rejects, which is maybe another
50%.
20.
50% of them are rejects, right?
No, but how many are clear rejects?
Oh, wait.
I'm assuming it's another 7% or so.
No, I think the clear rejects are 50% because if you see here, this number is high because they had to maintain the acceptance rate of 22.5%.
So what's the argument for the remaining roughly half to just not publish them all? If the process is evidently random for those middle half, just publish them all.
I mean, for this group, that's exactly what they did. But
what's the point of, otherwise for our conference, what's the point of arbitrarily rejecting, half the papers, right, that are subject to random review, evidently?
yeah, I'm more curious that did something change in the review process after this study came out? Like, have you seen any implications of this study ever? Any of the conferences later?
I think a growing realization that the process is random, largely, and you shouldn't read too much into people getting their papers published, and similarly, you shouldn't get too upset when your paper gets rejected.
Yeah, but then it's a design question, right? Like, how can we make this process better?
Except all the middle ones. If their current outcome is effectively a coin toss, just accept them all. Like, what's the argument for rejecting half?
Where did the 20% acceptance rate come from to begin with? You know? Did they just make that up?
They just made that up.
Yeah. I think most conferences have this. At least in CS, I have seen that they have some bar that, like, for every round of conference, the acceptance rates barely budge from one year to another.
Yeah, they're averaging over all.
Yeah.
But some conferences assert what the acceptance rate is going to be before they actually do any reviews, which I find odd.
Yeah. They are making an assumption that every year the quality of papers will follow the exact same distribution. Right.
And I guess none of this matters anymore because papers are obsolete as a medium of communicating science in this age of, agentic science.
Yeah.
So I guess it will soon be all over in this classical sense. I don't know what the new model is yet.
Gonna be interesting.
I think it can indicate that if your paper is not good enough, if you submit it to any conference, it will get rejected, right? Because according to the numbers we get, the paper get rejected to both conferences is actually a large proportion of all the papers.
Yeah, so most people submit bad papers. So don't be that person. Wait until your paper is ready.
Also, the acceptance rates are actually small, right? So papers being rejected by both conferences will be a large proportion, right? That makes sense. Yeah.
I think sometimes papers are also on boundary. Like, for example, I have seen this in my own case. Like, it's the audience that is reading your paper. So some people, like the experience that I had was the paper had more system details, and I was submitting to one of these human interaction conferences, and they're like too many system details. We don't like it. You want to do more human evaluations. And then the other conference that I submitted is more systemic nature. So they kind of appreciated the work that we have done.
I think it's also more on people's tastes.
Yeah, exactly. So that also plays the role. Okay.
All right, thanks a lot.
Yeah.
Now I have some data for you. Do I have some data for you? I do have some data for you. Thank you for sharing the slides. Post this stuff in the Slack channel. Okay, so you remember where we left off? Hopefully, we talked about these experiment designs for testing for multiple factors at the same time. So we talked about, the fully factorial design. For instance, we talked about Latin squares as a more efficient way of doing the same thing. But the idea is, there are multiple factors that we want to test simultaneously for. So we've had these different designs. So I have one here. Let's say we want to test the effects of experience and device on typing speed. This is sort of a follow-up to what we talked about in class last time, like testing different types of keyboards or things like that. All right, so surely the device should have some effect on, or does it? That's the question, on how quickly you can type. And similarly, there will be people that are more experienced typists, and they will likely type faster and so forth. And the novices should probably type slower. Right? So there's at least two factors. There could be multiple. There's at least two factors that we could design an experiment to test. So that's the setting. I shared some data. So let's start by actually looking at this. So first thing I'd like you to do, please, is to look at data set A. I shared two. Just start with the first one. We'll get to the second one later. Look at data set A and calculate the overall average typing speed for novices and experienced users overall, ignoring device and whatnot from the data set that I shared. Okay. And then do the same thing for devices separately, independently. So mouse versus start screen. Calculate the overall average typing speed for those. And then tell me about what your conclusion is about the effects of experience and device type on typing speed from this analysis. So just this. I would suggest you do this in R. You can do this in Python probably just as well. You could probably, but this simple part you could do in Excel or similarly, but we're going to do a regression or something like that in a minute too. So that may become more complicated to do in Excel. So maybe use, I don't know, R or Python or something like this to do this. And we're gonna build on this. I have a few more prompts coming up. So if you have taken some, I don't know, stats at some point, this should feel familiar. If you feel a little rusty on this part, you could try to read up a bit separately. I won't be teaching how all of these tests work and whatnot. Yeah, I guess I sort of assume that you can read up on this or that you have taken this before. If anybody wants to join the call and share their screen and show us what you're doing, that's also nice, or an option. Or the results of your t-tests. This I have actually not tried, so I'm curious. The result is a mystery to me as well. I'm guessing the differences will not be statistically significant here. But yeah, I haven't tried this. So maybe you can confirm. You've
6 developments and experienced and 0.9 for the mouse and touch screen.
Okay, yeah. So good. By the way, side note, if you have a well-designed experiment with randomized control, because of the strength of the design, that means there should not be many or any alternative explanations for the differences you're observing. You can be pretty confident in a causal effect there, right? We talked about this last time, which means when you get this kind of data as a result of an experiment, assuming there's no attrition and all the other things that we talked about that could go wrong, you don't actually need very fancy statistics at the end of this. Something as simple as a t-test is often sufficient because there are no confounding factors that could bias your estimates, right? Because the design of the experiment, right, controlled for all of these. So that's, like you have a good design and then you can use simple stats, or you have a less than good design or observational data or whatever, and then you have to compensate. You have to do a lot of work to compensate for that with, ever more fancy stats to make up for what you lose by not having randomization. Has anybody else ran a t-test? Andy? You're working on it? Okay. If Anmol, who was the first to propose that experienced typists are faster. Let's see if he agrees with your conclusion here.
Not significant, not statistically significant.
Okay, so they seem faster, but they're not statistically significantly faster. Okay. I'm gonna give you another minute or two. Rather, I'll come help you. Yeah, so tell me where you're stuck and I'll come help you.
So like t-test, there are like a few preconditions to run it, and one of them is that your data has to be normally distributed.
Yeah.
So you see that the distribution of typing speeds is normally distributed for novices, but not for experienced typists. So in that case, can you still proceed with the t-test?
Yeah, great question. So yeah, yes and no. It turns out the t-test is actually super robust to all these things. So in that sense, probably yes. But also you could run something else like ranked sum test or something like this, which would probably tell you the same thing. You could try that, like Wilcox or something.
Yeah.
Try something like that. And that would probably give you the same conclusion here. Yeah, who's stuck where? Let me help you. Okay. Good. Okay. Nobody's stuck anywhere? But that I could just leave then. Really? Okay. You all were able to run a t-test on these and conclude that the differences are not statistically significant. So to my last prompt there, what does that tell you about the effects of experience and device type? Like, let's say you've ran this experiment, that's the data you collected. You've now just analyzed it. What do you conclude for the paper?
Experience doesn't matter.
Experience doesn't matter, and does device matter?
No.
Nothing matters.
These two things doesn't matter.
But these were the two things that you were testing.
Yeah.
Experience doesn't matter, device doesn't matter.
I mean, that is probably going to be the next thing we estimate, right?
No, we're still staying here.
Okay.
Okay. So, you go through all this trouble, put in an IRB, recruit participants, are stressed about your advisor yelling at you to work faster, whatever. Do all of this, collect all this data. You're like finally super excited. You put it in R, and 5 minutes later or something, you conclude that none of this worked. So now you have this existential, crisis, panic moment, right? What have I done with the last, few months of my life, right? Okay. So next prompt. Let's run a linear regression similarly on this data, or an ANOVA, which is equivalent, where you include both predictors in the same model. So predict typing speed as a function of experience and device together. So something like, so if you're doing this in R, you could do something like speed as a function of experience plus device. You could do something like LM, and then you could do something like summary, oops, of this thing. And then here you could do data equals data A or whatever it's called. So something like this in R, I don't know what the Python syntax is. Something like this in R should work with the right names of these columns and data frame. Right, so now we are controlling for the effects of device when we're estimating the effects of experience and vice versa. Right, we're modeling this jointly. Which is stronger than what a t-test or equivalent does, because that's only bivariate, right? You're doing one at a time. Here, you're modeling everything jointly, so you're controlling for possible effects of, one variable on the outcome. So in other words, what you're doing is you're saying experience is beta 1 times, sorry, speed beta 1 times experience plus beta 2 times device plus epsilon. Now you're estimating this model and you're learning the coefficients that tell you what the nature of the relationship is between those variables and the outcome. So when you do this summary of the linear model call, it should tell you what the estimated values for these beta 1 and beta 2 coefficients are. And it should tell you what the overall p-values are for testing whether they're different from 0 or not, and it should tell you what the overall goodness of fit of that model is given this data. I would love for one of you that has done this in R to share your screen, because I don't have this ready, and actually show me the output here so we can talk about it.
I think there's a similar library in Python as well, the stack model library.
Quite possibly, yeah.
Yes.
Does it give p-values?
It does give you.
Do you want to, can you join and share? Do I have to stop sharing so you can share? Yeah, nice. Okay, perfect. So this should be equivalent to what you're getting in R, I assume, on this data set. So you're getting the coefficients for the two variables that have been estimated, and you're getting whatever's left over, the error term, the intercept. This is called the intercept, whatever's left over, right? So the equation is the one I showed, this thing times experience plus this thing times device plus the error term. Okay, linear combination of these variables. You're estimating the coefficients. The coefficients are, I guess we don't have the coefficients, maybe in OLS here.
Yeah, here.
Yes. Okay. Good. So. Okay. The other thing. So these are both categorical variables, right? They have two levels each. Each of these variables can be either novice or experienced in this case, or touch screen versus mouse in this case. Right? So when this happens, one of them is necessarily the reference category, the baseline value for this. right? Novice equals true here suggests that the baseline value of this is experienced. So, by default, this variable is experienced. And if you switch from experienced to novice equals true is I think what this means. So going from experienced to novice increases your typing speed by 0.92 seconds or something. Is the way to read. I hope that's the interpretation of the right interpretation of this. I don't know the syntax for this Python library.
Yeah,
Is that
I
right?
used it way before once. I'm also very heavy on reading.
Does anybody have the R version to confirm? Is that the same?
We have the same value in using the same library and the same everything, so.
Okay. Because I thought you said experienced people are a little faster.
Nice.
Oh, that's right. So I see. Right. So novices are about 1 second slower.
Yeah.
Yes, that's right. So this is correct. Okay, good. So note how when we're drawing that conclusion, we are holding fixed all of the other variables in the model, which is why this is a great, modeling framework. It's better than a t-test because it allows you to hold constant all of the other variables that you plug into the model. In this case, device is the only other variable we have in the model, and we are assuming device is held constant at its base level, which is a mouse, right? So when device is mouse, going from being experienced to being a novice is about a second slower. Okay, that's the interpretation of something like this. And then you look at the p-value for these coefficients. So this tells you if this estimated coefficient is statistically significantly different from 0 or not. Okay, so because the p-value is very high, you cannot reject the null hypothesis that the coefficient is indistinguishable from 0. Therefore, you conclude that the coefficient is indistinguishable from 0, and that there is no correlation between experience and typing speed. Okay? Same for this one. Whatever the estimated coefficient is, you're assuming experience here is held constant at the baseline value. The baseline is experienced. And this is similarly also not statistically significantly different from 0. Therefore, there is no statistically significant association between these variables. Therefore, there's no effect of device on typing speed, according to this analysis, right? So none of this is new from what we've seen before. It's just a more rigorous way of testing the same thing. Okay. So by the way, speaking of this, why do you think experienced was chosen as the baseline here? That you didn't do that explicitly, right? And similarly, why do you think mouse was chosen as the baseline?
Let's look at this.
You know?
I guess it just wanted to make the coefficient positive.
No. It's much dumber than that.
Distribution.
No.
Alphabetical?
It's alphabetical. It's always alphabetical. Okay, so this actually often does not make sense. So you yourselves should set the appropriate baseline level for these categorical variables, and you could do that as part of the the model, right? So you should decide which one is meaningfully the baseline, so that you can interpret these things in a way that makes sense for the problem you're studying, right? So here, this interpretation does not make sense, right? Because you don't. you go from being a novice to being an expert. You learn, right? How to type better, right? Not the other way around usually. So these two do not make sense. So here, absolutely, I would say, flip the baseline so that you can reason about the right direction. Mouse versus touch screen probably doesn't matter. It's like both make sense. So maybe you have a hypothesis in your study, right? Maybe you chose one as the baseline because it was whatever prior work did before you, and you're the first to introduce a touch screen. So it makes sense to set mouse as the reference because that's the old way of doing this. You test the effect of your new thing, right? So, but in any case, this is a choice you make deliberately. Otherwise, you end up with the alphabetic ordering, which is silly. Okay, the other thing, how well does this model fit? Is there a measure of goodness of fit?
Should over here.
Yeah. So these ones, can you go down a bit? Yeah, so over here, so basically not at all, right? This is a measure that should go up to 1, between 0 and 1. So you're as close to 0 as it doesn't matter. So, your model doesn't explain anything. Model doesn't explain anything, and there's no effect of any of these variables. Right, so we're back, we're still in existential crisis mode, what do I tell my advisor, sort of thing. Right? Okay, good. So let me go back. Let's see if I can share again. I can, turns out I can just override you. Okay. Good. Oops, go away. All right, now, why don't you visualize the data? So just create a line plot or an interaction plot with experience on the x-axis and typing speed on the y-axis and separate lines for device. There you go. Whoa, what just happened? Well, look at that.
Well, novice is on the right again, so it's also it's kind of a little misleading.
That is annoying, I agree, yes. It's probably the same problem as before. They have to be reordered.
Interesting part is these are two different libraries, not even the same library that I'm using.
So I guess the alphabetic thing is the universal thing. I mean, just ask your chatbot to reorder the levels. Yeah.
Want to know why.
Device doesn't matter too much, but experience should be novice first. So what happened? Like, what is this? Yeah, what's going on?
Combination factors.
Right. The novices perform better with a mouse, but novices perform better with the touchscreen, experts perform better with a mouse.
Yes. So we ended class on Tuesday with this notion of asymmetric skill transfer. This is, I guess, perfectly anti-symmetric skill transfer. But it's never this clean in reality, right? This will never happen. This is all artificial, right? You can get something this clean. But the point is, your study is not lost. It's not, all hope is not lost. You can go back to your advisor now because you've discovered something really interesting, right? The time you spent running this experiment was not wasted because there are very strong effects here, right? They just are not visible if you look at the averages, right? Very strong effects of both device and experience, just they cancel each other out. They're in opposite directions. Do you see that? Okay, so now how do we show this to your advisor? How do we show it? How do we show this statistically?
Even like, statistically, sure, I like do.
Yes.
We add the interaction variable as another.
Yes, so that is the missing piece here, the thing that we did not do. Let's kick Prasoon out again. We talked about this. Okay, so that means do something like the following. I don't know what the Python syntax for something like this is. This is what it would look like in R, or alternatively, the shorthand would be the following. Experience times device. This is what this would look like in R. So now we're adding an interaction term between these two variables, right? I used two M words maybe last time. I talked about mediators and moderators. Do you remember what those were? What were they? Marco.
I believe the mediator, I don't remember, I don't remember which one is which, but one of them is, let's say you have A, B, and C. A goes into both C and B, and then C goes into B.
Yep.
I think that's a mediator.
Yep.
Okay.
I did preface by saying these are confusing, which is why I'm teaching you about them last time.
Yeah.
Yeah.
And then the other one is like A, B, C. C goes into both A and B, and then A goes into B.
Not quite.
C moderates the effect of A on B, whereas the mediator can explain the effect of A on B to varying extents.
Right. So the moderator is what's going on here, right? C moderates the effect of A on B, right? The effect of experience on typing speed is moderated by device and vice versa. Okay? So the way to test that is by looking at literally the product of these two variables. Okay? So I guess we'll get Prasoon back on the screen in a second if he has it. So if you have not seen this firsthand before, if you've not done this kind of model before, a world of possibilities has just opened. Your future now in empirical research will never be the same. It's very exciting. Next time you read a paper that has some, I don't know, like statistical analysis of data or some regression or something, look for interaction effects in their discussion or their model.
And if they don't have them.
Well, you don't always need them, right? We have a hypothesis here that there is a moderator, right? So you include interaction terms, you model interaction effects when you hypothesize a moderator effect. You don't usually just test them just to check.
Sure.
Unless it's an exploratory study or something.
So I think probably you might have to go to the Zoom and then if we both can share together.
What?
Yes.
What do you
So
mean?
Go to the Zoom again, the screen.
Only if I stop. You cannot kick me out, it seems.
Yeah.
So you have it?
I don't know what these things are. I'm trying to figure out.
Where are the okay, go down a bit. Okay, so this is the thing.
Yeah.
So look how interesting. So now, we still have coefficients for the first order effects, just like we did before. because turns out you cannot interpret this in isolation. But we also have a coefficient for literally the product of the two things, the interaction term. And now all of these are highly statistically significant, and your model fits very well. Okay, look at this. So you have a well-fitting model, right, that captures the variation in your data well. This is a very high value, it's close to 1. You will rarely get values this good on real-world noisy data for stuff like this, because there's a lot of noise in these measurements. So this is showing okay, so going from novice to experience. Okay, so device equals mouse by default, right? So if device equals mouse, this is 0. If device equals mouse here, this is also 0.
Yes.
So then when device equals mouse, going from novice to experience gets you 9 seconds, or 9 characters per minute faster speed. Sorry, slower speed. Is that right? Show me the plot again. When device equals mouse, so that's the blue line, going from novice to experienced, so going up on the blue line, gets you about 9 characters per minute. There's a speed, so it's faster. Higher is faster, right? Because you're going from about 20 to about 29. Okay, go back down to the thing. All right. Now, we could do the same math for the other thing. If experience is novice, the baseline, this is 0 and this is 0. So for novices, switching the device from a mouse to a touch screen speeds you up by about 10 seconds. Sorry, characters per minute or whatever, words per minute.
Yeah, this. Yeah, because they will come out.
Yeah, so for novices, switching the device
To touch screen.
gets you about 10 characters per minute faster. Okay, so this is how you read these coefficients. Okay. Yeah, all right. Does that make sense? Make sense? And similarly, you can read the interaction term coefficient to look at this crossover effect. Okay. All right. Questions on this? This is really critical. You have to really make sure you understand this part. This is going to come back forever from now on. Now is the time to ask questions. Question?
So the P for the experience and device also changed.
Yes.
That was surprise for me. Why? Is it because we are trying to add the interaction term? That's why those coefficients start mattering.
Yes.
That was me.
Yes, because so your previous model, if you remember, did not explain the data at all, because you had not modeled this crossover effect. The new model is fancier, right? Better captures the variation, the process that generated the data, the variation in the data. And now all of these variables have significant coefficients, meaning there are first order effects for these as well as an interaction effect between them. Okay, so now your advisor is happy, right? Because you have a story. In fact, it's an interesting story. So please ask anything about any of this. Now's the time. Okay, then let's do a quick one. Let's see. Kick person out again. The quick one is the following. Let's look at the second data set now and do this thing again. So you can directly run a regression similar to the one we have just run, but make sure you visualize the data as well. Good? Clear?
Oh, yeah.
Okay, with the second one? Okay. That was super fast. Show off. By hand or with the?
Mostly by.
Show off. You have a plot? You wanna join the call?
Sorry, where's this?
I don't know. Somewhere. Oh, actually, I can invite you.
Difference between these two data sets, just they're differently generated.
The effects are different.
Do you use this one library or not?
I use C1.
There's
I
only
also use that.
there's only one correct answer. Neither of these is the correct answer.
Okay.
It's hard.
You should only ever use GG plot two. There are plotting libraries, GG plots too. Anything else is not acceptable. I'm serious.
I unfortunately just don't know how. That's a big learning curve for right now.
Or your agent will do that for you. I think seeing a matplotlib or something plot in a paper is equivalent to writing a paper in Word to begin with instead of LaTeX. It's like that's striking a difference in aesthetics.
Did you know that Christian Kastner writes his papers in Word and then has a library that reprints it from me?
I did not. Whenever I worked with him, we directly edited the thing forwardly for.
Apparently not anymore because my office mate is required to write all of the papers in Google Docs
Wow.
and then export it to Overleaf.
Oh.
And so I don't want to.
Again.
Again, tell him I don't want to make Google first use Google Doc.
So that's probably not about LaTeX per se. I think he just doesn't like overly. I think he likes LaTeX, just not overly. So it's sort of the collaboration aspect.
Are there libraries that can convert Google Doc to LaTeX?
Not use as a.
Oh, really?
I don't think they should just. You should just.
You're done? Okay. So can we see a regression also for this? So but first off, before regression, what's the story? Let's look at the data a bit. Yes, what's the story here? How would we interpret this? So let me ask differently. Is there an effect of device on typing speed?
Yes.
And we can tell this because the slopes are different. So like if they were the same, then the only difference would be the like quote unquote intercept between novice and experienced.
I would say no, we could tell because the levels are different.
What do you mean?
So device is blue versus orange. So because orange is in a different place than blue, on the y-axis.
Yeah, that's what I mean, the intercepts.
Oh, sorry, I thought you said slopes. I
No.
misheard. I agree with your characterization. My bad, sorry. Yeah, so yes, okay, there is an effect of device. Is there an effect of experience? Yes, experienced people type faster than novices.
In different rates for different devices.
Right, so that means there's also an interaction effect. Right, just not a perfect crossover like before, which will never happen in practice. This is a much more realistic scenario, right? Something like this will happen in practice. And so there's both an effect of device and an effect of experience and an interaction term here, right? The people that improve the most. So device, like if you read it this way, device moderates the effect of experience on typing speed. Right? The effect of experience on typing speed is positive, right? More experience means more typing speed in both conditions, but the slope varies by device, right? So it's a greater increase for the mouse than it is for the touchscreen in this case. Okay, so now do we have a regression confirming this? So I guess I will leave this as an exercise to the reader and maybe quiz you or something later. You should figure out if you can map these coefficients back to what we're seeing in the plot. Being able to interpret these coefficients is crucial because we will be working with very highly dimensional data most of the time, and you will not be able to plot it in the same way. So you will often just rely on these interpretations of the coefficients to tell a story. So make sure you can get from here to what the data actually looks like. Okay. Okay, good place to end for the day. Hopefully you've seen how to analyze some of this experimental data that would come out of a factorial design of an experiment. Okay, great, very good. Thank you all very much. I will see you next week.